So looking at part 2 of chapter 4, we're going to focus on the energy and power portions.
So what is energy? Energy is the ability to do work. James Joule actually established this definition of energy by conducting some experiments. So in order to calculate energy, you need to know the force as well as the distance. When we calculate energy, the units are going to be joules after James Joule, who did this pioneering work. So work is done when a force is applied to an object and it moves that object. So when we calculate work, we're going to look at two different types. We're going to look at linear, so shown in the example picture, where a person is pushing a crate across a certain distance, linear. We're also going to look at vertical work, and this will be picking something up. Okay, so if you are picking up a box and setting it on a table, picking up grocery bags and setting them on the counter, this would be vertical work. You are lifting something up. So to calculate work, we need to know the force applied to that object, but we also need to know the distance that that object moved. So for linear work, it's going to be the force applied in this picture, this green vector here, times the distance that crate was moved. For vertical, the force we're looking at is going to be the weight force, because when you pick something up vertically off the ground, what's affecting that object is gravity. So that's why we're looking at the weight force here. And then you're also going to be looking at the distance. How high was that object lifted? How far? So work is a vector quantity. So it has a magnitude, but it also has a direction, right? For vertical work, you are lifting that object up in a certain direction. The units are going to be joules because work is a form of energy, and all forms of energy are going to be measured in joules. Now, if the object does not move, the work done on that object is going to be 0, because it needs to move a certain distance in order for any work to be done. So looking at the examples below, on the left, we have a person using a 500 Newton force and pushing against this object here, this boulder. However, the object is not moving. So the work that this person is doing is 0. They are doing no work. Even if they're sweating and they're pushing as hard as they can, and they're using their muscles, they are actually doing no work unless that object moves. Now the person over here on the right is also applying a 500 Newton force, but the object does move. It moves 6 meters. So this person is doing work, and we can calculate how much work that person is doing by taking their force of 500 newtons and multiplying it by the distance they moved that boulder, 6 meters. Now in this diagram here, there's also no work being done, because you need force and distance to be in the same direction in order for work to occur. Okay, and the force that is being applied is upward. It's going in the upward direction, right? Lifting that box up. But the distance is going in a different direction. It's going linear, right? They're walking forward. So no work is being done because an upward force is being applied and a linear distance is being covered. So therefore, their work is 0. We need both force and distance to be in the same direction. We have distance in the y and force in the x. Let's look at a different form of energy. So kinetic energy is called moving energy. So if an object is in motion, it has kinetic energy. To calculate kinetic energy, we're going to be using the following equation, 1/2 mv squared. M being the mass, v being the velocity. The term kinetic is actually Greek for motion, because kinetic energy, like we said, is moving energy. All objects in motion have a kinetic energy. Once this arrow is loosed, it will have kinetic energy. Right now, that object, that arrow, has a certain amount of potential energy, and that's what we're going to look at next. So what potential energy is stored energy. So all objects that are not moving have a certain amount of potential energy, of stored energy. This is energy that is available to be released. When we look at potential energy in this chapter, we are going to focus on gravitational potential energy. So what that means is objects that can fall, essentially. So if we're looking at gravitational potential energy, we need gravity. So gravity, 9.8 meters per second squared, will be used in these equations. So we're going to take the object's mass in kilograms, the gravitational pull on that object, multiplied by the object's height in meters. So we will look at the potential energy of objects in trees that have the ability to fall to earth, or objects on a countertop or a table. Okay, so it's going to focus on objects at a certain height that have the potential to fall. So potential energy and kinetic energy are closely related, because potential energy is the stored energy of an object that is not in motion. Once that object starts moving, that potential energy is converted into kinetic energy. So the example of a balloon. So you have a balloon filled with air. It's not moving. That balloon has a certain amount of potential energy, stored energy, and that's the air that is trapped inside the balloon. That's its stored energy. When you let that air out of the balloon, what happens to the balloon? It starts moving. Okay, so now that it's moving, that potential energy, that stored energy, is converted into kinetic energy, moving energy. Another example, say if you're at the top of a hill on a bike, and you're not moving, so you have a certain amount of stored energy. Once you start going down that hill, once you start moving, that potential energy is converted into kinetic, moving energy. The higher the hill, the higher the potential energy. Right? That's that distance, that height portion of the equation. Some calculations that we're going to be looking at in the video posted on work, kinetic, and potential energy. I want to point out that all of these are going to be measured in joules. So work is a form of energy, so it will have the units of joules. Kinetic and potential are also forms of energy, so their units will also be joules. Make sure you are checking, converting if necessary, and then plugging into the equation. Here's just another example that we'll be looking at. So let's look now at the conservation of energy. Energy cannot be created or destroyed, but can be altered from one form to another. So an example of this is potential energy being converted into kinetic energy once the object's in motion. So due to the conservation of energy, we can actually set potential energy, PE, equal to kinetic energy. So what I have here is the equation for potential energy, mgh, set equal to the equation for kinetic energy, which is 1/2 mv squared. So in this diagram below, we have a person holding a ball over the edge of a cliff. That ball's not moving, so it has a certain amount of potential energy. So let's say it has 12 joules of potential energy. Say I calculated it and it has 12 joules of potential energy. When I drop that ball, that potential energy is going to be converted into kinetic energy, moving energy. Well, since potential energy and kinetic energy have to be equal to each other due to the conservation of energy, that 12 joules of potential energy is going to be fully converted into 12 joules of kinetic energy. So if you are talking about a specific object, whether it be a ball, a bird feeder, an acorn in a tree, an iron on an ironing board, its potential energy is going to equal its kinetic energy if it falls. Now let's look at power. So power is the rate of doing work, the energy transferred. So when we calculate power, we're going to be taking work and dividing it by the time it took to do that work. And since work is a form of energy, we are basically taking energy, how much energy was expended, and over what period of time that energy was expended. Now James Watt defined power when he replaced horses with steam engines. So when we calculate power using this equation, it will be in watts after James Watt. So just capital W for watts. We will also be using a conversion factor in some of our problems where we are converting between horsepower, HP, and watts. So you'll notice on your equation sheet, this conversion factor is underneath all of your power equations. So if you need to go between watts and horsepower, you will be using the equation 1 HP is equal to 746 watts. So for power, there are several different equations because we said power is energy over time. And we talked about 3 different forms of energy: work, potential energy, and kinetic energy. So that's why we're going to have several different equations. Work, kinetic, and potential energy are all measured in joules since they are all forms of energy. Time needs to be in seconds when put in these equations. If we're using this last equation here, F is equal to V average, F is a force, and the force needs to be in newtons. VAV means average velocity, and velocity for all of our physics problems needs to be in meters per second. The next few slides are just showing how those equations on your equation sheets are formed. So the first equation for power is work over time, and we said work is force times distance. So that's how we get power is equal to F times D divided by T. The next equation on your equation sheet is representing kinetic energy divided by time. So to solve for power with kinetic energy, you're going to take the mass in kilograms times the velocity squared, don't forget to square it, and divide it by 2 times T. Potential energy equation relating to power. Potential energy, we said, was mass times gravity times height. So we're going to take mass times gravity times height and divide it by the time to calculate the power. So since there are several different equations for power, you're going to have to use clues in the word problems to figure out which equation is going to apply. So for this first one, calculate the power of an 18-kilogram dog that climbs stairs 5 meters high in 20 seconds. So we have mass, we have a height or a distance, and a time. So you're going to go through your power equations and figure out which one applies, which one has mass, height, and time in it. Once you find the appropriate equation, you can plug in your variables and solve. So I have a video showing me going through all the steps and calculating these exact same problems, starting with converting if necessary, writing the knowns and unknowns, and then picking the appropriate equation.